basically, let's say, the smallest unit of CPU utilization, or the basic unit of CPU utilization. And each thread, like every other process, will have um, a thread ID, a program counter, a register set, and a stack. Okay, and like the child processes that we have seen in the last chapter, it could share resources with the parent process, and it could share the same memory space or not with the parent process. Okay, and similar to that, the threads, it can also share resources with the main process, given that it is a thread of the main process. Okay, that means if a process does not have any threads, and let's say there is another process which has 5 threads, so those 5 threads will be sharing resources with its parent process, not the other one. Okay, and why do we need threading basically? Now, a very intuitive example of this is that whenever you basically are using a web browser, what happens? You could open a lot of tabs at the same time, right? And you could basically, let's say, browse for something in one tab, as well as you could listen to some music on the other tab, right? As well as you could, let's say, download something using another tab or a background process. Now, all these processes, whenever you're, let's say, browsing, does your browsing hamper how audio is played on the other tab? Okay, so the first rule of online classes is whenever I ask a question, you should respond. Okay, otherwise, I could just mention which topics you need to read and then just end the class. You understand my point?
Yes, sir.
Okay, so as I was asking, so you're browsing in one tab and listening to music on the other tab. So, does any of your activities hamper one another? If you're browsing, does it hamper your music? Or if you're listening to music, does it hamper your other activities on the web browser?
No, sir.
So, it doesn't. So, which basically means is that each tab that you create on a web browser is basically a thread or a sub process running or run by the browser itself. Okay, again, let's say you're downloading parallelly while working on your let's say web browser. Okay, so this download activity, it does not hamper your other activities on the web browser as well, right? So this download portion is, I mean, it's possible to say that it's a threaded process as well, because if you have a single threaded process for a web browser, what would happen is you would find that your web browser has become unresponsive. Why? Because whenever your web browser is executing another task, it basically is uh, executing in a blocking mode. That means it will not respond to any sort of input from the user before finishing the task at hand, right? So to, I mean, resolve these types of issues with graphical user interface interactions, the threaded architecture or multi-threaded programs are mostly used. Okay. Also, it ensures the concept of concurrency and parallelism at the same time, which we have already, let's say, discussed so far in the previous classes. Okay. And the example of web browser that I gave, another example could be is that a server which is, let's say, listening for user requests at a certain port, and whenever a request, let's say, comes in at that particular port, the server will not basically dedicate the entire process, or it will not dedicate entirely itself to handle that request, because if it does so, other users cannot simultaneously send requests to the server, right? Now, the fact is, what could happen is, thread and sub processes, there is a little difference. For example, uh, your server, when a client request is, let's say, sent to it, it could create a sub process rather than a thread. Okay. However, creating these sub processes is more, uh, resource consuming or time consuming, or you could say creating a sub process has more overhead compared to creating multiple threads. Okay, this because with threads, what you can do is something known as thread pooling. That means you will have active idle threads. By that I mean threads which have already been created, but no particular task has been assigned to it. Okay, so these active idle threads are basically kept in a, let's say, um, a stock, not a stack, it's a stock of threads. Okay, so whenever a new request comes, the client request could be delegated to one of the threads from that particular thread pool. Okay, that's one way, that's the most efficient way. Another option could be, you could create a thread as per the client requests. Okay, because you want to, let's say, ensure that the number of threads available in your system does not, exceed the amount of requests that your system receives, because that at some times could be, let's say, uh, more resource consuming. Okay, or it could add more overhead in terms of creation and maintaining and distributing resources. Okay, apart from this, another example is in the RPC mechanism that we saw in the last chapter, where you saw that you had various stubs, right, from on the client side and on the server side, which were responsible for marshalling and unmarshalling parameters for data exchange or information exchange between the stakeholders, right? So these stubs basically are threads. Okay, and they play a very vital role, as we have already seen, because in case of server client communication, the first thing that you want to minimize is the latency of communication. And if you don't do that, the user might find, uh, i mean uh, discomfort in using that particular web service. Okay, now if you look at this particular figure, it says that whenever the client will send a request to the server in step 1, the server, what will it do is it will create a new thread which will basically serve that particular client's request. Okay, in step 2. And once that creation and delegation of task is completed, the server will resume listening for additional clients, right? So um, that's basically the overview of how the client server communication can be handled using threads. Okay, and what are the benefits of it? As I have discussed a few of them in these examples. The first one is responsiveness. And I think I gave this example that whenever you want to ensure responsiveness of graphical user interfaces, threading has, no alternative, right? So if you have a graphical user interface, and let's say it is not multi-threaded, right? So a user will click a button, let's say that will result in some time consuming task. Okay, so until that particular task is completed, the control will not be returned to the main program, and hence, until that control is returned and you click another button in the meantime, you will find that your button is not responding, and that leads to user dissatisfaction with unresponsive UIs, right? And that is why if you have, let's say, a threaded architecture, so if it, let's say, performs that time consuming task as part of a thread, and you have the user interface to serve other user actions with other threads already created or will be created as per request. This will ensure that your UIs are responsive and the user feels that the interaction is real time. Okay. The second one is um, resource sharing. Okay. So the processes, they basically can share these resources as, and these are shared using the techniques that we have discussed earlier. It was either using message passing or shared memory, right? But the threads, unlike processes, share the memory and resources of the process to which they belong by default. If you consider the case of child process, and we saw that the child process could share the same uh, memory space or a different memory space, right, with the parent. But in case of threads, the same memory space and the resources of the process to which these threads belong will be shared by default. Okay. And that basically allows us to utilize the concept of shared memory access. Okay. And it reduces the latency of communication. The third benefit of using threads is that whenever you create a process, not a thread, whenever you create a sub process and you allocate memory and resources for that sub process, it basically is more costly, or it is costlier than doing the same for threads, because threads share these resources and memory space by default, whereas you have the option to um, let's say share or not share the same resources or memory space in case of child processes. Okay. And in the very beginning of this course we talked about a concept called context switching. Can anyone tell me what context switching was? What is context switching?
স্যার ভুলে গেছি মানে
ভুলে গেছো তো? কুইজ কুইজ দিবা কেমনে? মানে তোমাদেরকে আমি ক্লাসে যে জিনিসগুলো পড়াই এগুলা কি তোমাদের তো একটু দেখা উচিত, তাই না? উইদাউট দিস কনসেপ্টস, এগুলোর যদি ক্লিয়ার আইডিয়া না থাকে, then what is the point of attending the consecutive classes? Anyways, so context switch basically means is whenever you shift execution from one process to the other by halting the previous process, and this involves saving the current state of the previous process to its PCB and reloading the previous state of the new process from its corresponding PCB. And this is known as context switch because the CPU is moving on from a different execution environment, from one execution environment to the other. So the context is changing, and hence it is known as the context switching. And the fourth benefit that we'll have with multi-threading is scalability. So you can have, let's say, multiple processors, right? If you have a multi-threaded architecture, if you add more cores to your processor, your multi-thread facilities will increase in that manner. Okay. And let's say if you have a single core processor, it means that, or a single threaded system, it means that you can only run a single threaded process on only one processor, and it does not matter how many process you have, how many processing cores you have. So in long story short, in terms of scalability, if you have a single threaded system with multiple cores on your processor, each core will be able to run only one thread, okay, no matter how many cores are available to you. But if you have a multi-threaded architecture and multiple cores in your processor, then what will happen is each core will be able to execute multiple threads, ensuring scalability of your system, right? And um, we talked about parallelism and concurrency, right? You remember what parallelism and concurrency was? নাকি এটাও ভুলে
Yes, sir.
গেছো?
Yes, sir.
আচ্ছা, so if I rephrase, if you have, let's say, two processing cores, in this case, if you look at figure 4.4 here, you have two processing cores, core 1 and core 2, and on the x-axis you have your time elapsed, okay? So what you do is you assign two processes, T1 and T3 to core 1 and T2 and T4 to core 2. So when core 1 is executing T1, it basically cannot execute T3, right? But whenever core 2 is executing, sorry, core 1 is executing T1, core 2 can execute either of T2 or T4, right? So let's say it executes T2. Again, if you have a scheduling algorithm which, let's say, assigns particular time slots to your processes, so after the first time slot here, the second time in the second time slot, the other process or the same process may get the CPU. Let's say in this case, the other process gets the CPU. So in core 1, T3 will get the CPU, and in core 2, T4 will get the CPU. Now, the thing is, the amount of progress T1 is making in core 1, let's say theoretically, T2 makes the same progress in core 2. So this setup or this method of execution is known as parallelism. That is, these two processes or these two tasks are progressing by the same amount at the same time in two different processing cores. So that is parallelism. So parallelism occurs in the vertical axis. Okay. Now, if you look at both of these cores, now T1, it proceeds, let's say, by 10% in the first slot. In the second slot, T3 will proceed by the same amount, let's say 10%. But this switching in modern computers happens so fast that the user basically does not get an idea of whether these two processes are running parallelly or concurrently. That means the concurrency of these processes, that is, two processes which proceed or progress by the same amount subsequently, okay, not at the same time, subsequently. So the latency between these progresses is so minimal in modern computer systems that it can easily be mistaken as parallelism from the user's perspective, okay. So the concurrency that happens in multi-threaded multi-core processors is along the horizontal axis, okay. So this is basically the concept of concurrency and parallelism. Now, since we have the concept of parallelism, that means you could have a process which executes certain instructions in it parallelly, while certain instructions need to be executed serially. An example could be that if you consider the application rule for linear algebra, are you familiar with this? Are you familiar with this theory? Bracket of division, multiplication, addition, and
Yes,
subtraction.
sir.
Okay. Now, what if, let's say, you have a plus b minus b by c plus, let's say, C times D. Now, can you tell me which tasks can I do here parallelly,
A plus B, B by C, and C into D.
right? So these, whatever tasks are there in these brackets, they can be parallel tasks, right? Task parallel 1, task parallel 2, and task parallel 3. Now, what are the tasks that I cannot do parallelly? Rather, I'll have to ensure a subsequent or serial execution. I'll
The
have to do
addition
the
and
addition first,
subtraction.
right? Task serial 1, and then I'll have to do the subtraction, which is task serial 2. So now what the thing is, you could distribute these um, activities into different processing cores, okay? Parallel tasks and serial tasks. But the question is how you distribute and among how many cores you distribute these tasks will allow you to determine your processing speed up using a certain law which is known as the Amdahl's law. Okay, and this Amdahl's law basically gives you the speed up, an idea of the speed up, as this particular formula, which says speed up is less than 1 upon S stands for the serial part of the application represented in percentage, and 1 minus S represents the parallel part of the process, again represented in percentage, so that the summation of S plus P is equals to 1, right? So if you look at this example here, how many tasks do I have? 5, right? Among these 5 tasks, how many tasks are parallel?
3.
3. So 3 by 5, you have parallel tasks, and serial tasks is
2
2
by
by 5,
5.
right? That means if you have S equals to 2 by 5, P will be 1 minus S, or 1 minus 2 by 5, which gives you 3 by 5. Now, if you express this as decimal, let me give you a real demonstration. Just a minute. Okay. If you look at the example, what was the formula? 1 over the serial portion, right? What was the serial portion?
2 by 5.
2 by 5,
5.
right? And then you have plus 1 minus, again, the serial portion.
3
I'm
by
just
5.
breaking it down, but you could definitely, let's optimize the calculation. I'm just making it easier for you. Now, let's say you have, I mean, in the formula you see here, the value n basically indicates the number of processing cores that are available to you, right? And what I'm trying to demonstrate is, let's say you take 2 processing cores, okay? And in that case, your speed up is 1.43, right? Now let's say you use 5 processing cores. The speed up would be 1.92. What if you use 50? 2.42. 500? 2.49. 5000? 2.499. Now, can you see what is happening here? As I increase, the value basically approaches what? A maximum value, right? 2.5. After that, no matter how many cores you add, it does not increase the speed up. Do you understand? I mean, can you visualize what's happening here? So it does not always necessarily mean that you can increase your processing speed to an infinite value by just increasing the processing cores. There will be a theoretical or a practical maximum value beyond which your processing speed will not increase. It's like having the maximum speed set to 180 in your let's say car's odometer, okay, or the speedometer. So this is the working principle of the Amdahl's law, and it says that um, the value of n that we saw, or if we used here, let's say it was more than 50, 500,000, we can consider it that it is approaching infinity in this particular example or in this particular context, right? So as this value of n approaches infinity, the speed up converges to s, 1 upon s. Can you tell me why? Look at this. In this example, you are dividing 3 by 5 with such a big value that it becomes a negligible value. Okay, and that is why with the value of n approaching infinity, the speed up of your system will converge to 1 over s, n approaching infinity. Is the idea clear to you?
Yes, sir.
Okay, and that is why this example basically illustrates that the serial portion of any application can have a disproportionate effect on the performance that we gain by adding additional computation cores, right? And let's say, although it does not take into account the hardware performances, but it gives you a basic idea of how parallelism and parallel and serial execution of different tasks can let's say speed up the process, or let's say reach a maxima. Okay, now there are a few challenges whenever you're dealing with multi-threaded um, system or multi-threaded frameworks. Okay, the first one is identifying the tasks. Okay, um, because as you see in this example, what we did was we identified which tasks could be divided into serial portion and which could be divided into parallel portion, right? Based on that, you will be let's say defining threads or introducing threads to your program execution. That's why this says that identifying tasks involves examining applications to find areas that can be divided into separate concurrent tasks. Okay, ideally, tasks are independent of one another and thus can run in parallel on individual cores, but it's not always the case that we have seen in this particular example. The second challenge is balance. So let's say if I try to um, distribute tasks P1, P2, and P3 in three different cores, I mean, it should not take much time, right? Because these are very simple tasks, right? So a simple concurrency could have solved it. However, if there were, let's say, three different tasks which you intend to execute in parallel, but the volume of execution of these three tasks are not the same. That means one has a huge work to do, the other has a medium level, the third one has very little work to do. So in that case, you could uh, ap- I mean, apply certain optimization techniques so that these processes could be, let's say, two processes could be done concurrently, while the process with very large amount of work could be handled on a separate thread, right? So that is why it is very crucial that you ensure balance while distributing parallel and serial tasks in your multi-threaded architecture. The second is, the third point is data splitting, how you divide the data into these tasks so that you don't run into any synchronization issue. If you remember the example of the count variable, right? It had a value of 5. Without proper synchronization, one process incremented its value to 6, while the other process decremented its value to 4, but which actually should have been 5 after each of these processes operation, because the count variable was shared between these two processes. Okay, so that is why you need to ensure data splitting very carefully. And data splitting and data dependency also, I mean, are correlated. As we can see, it could lead to these types of synchronization issues. And finally, we have is testing and debugging. If you have a single threaded program, you could test and debug errors as easily as you can. But if you have a multi-threaded architecture, what will happen is you might be, let's say, you might feel lost as to where this particular error is being created. Okay, and that is why you need to keep track of these errors and debug them appropriately when you are dealing with multi-threaded architectures. Now, since we are talking about parallelism, and this brings us to the types of parallelism, and there could be two types of parallelism. One is known as the data parallelism, and the second one is known as the task parallelism. Now, what is data parallelism? Let's say you have an array of integers 1 to n, right? And in case of data parallelism, you basically divide this array into, let's say, two halves. Okay, and it could be just a minute, from 1 to n by 2 minus 1 index, and the other one could be n by 2 up to n minus 1 index. Okay, so whenever you divide your data into subsets, okay, and the threads that you are dividing this data into, they have to perform the same operation on these two subsets of the data. Whenever you can allow that, you have ensured data parallelism, and these two threads would be running on two separate computing cores, since we're talking about parallelism. So data parallelism is, long story short, you distribute subsets of the same data across multiple computing cores and perform the same operation on each of these cores. That is data parallelism. Now, in case of task parallelism, what could happen is you're not going to distribute data, rather, you're distributing tasks across multiple cores. So, if we look at our previous example, what type of parallelism is occurring here mostly? Can you guess?
Task.
Task parallelism, right? Now, if you look at the distribution of these variables, is there any possibility of data parallelism happening here? Do you find any possibility of applying data parallelism here? No, right? Because these are single values. Now, what if you had, let's say, an array of numbers, and these were given in relation to those array indices? Then you could have said that, okay, for every subset of the data, these operations are carried out in these two subsets simultaneously. In that case, you could have said you were applying data parallelism. But here, since that is not the case, you're distributing tasks across processing cores on the same data. That is, you are applying task parallelism. Okay, so the task parallelism is ensuring that you have a unique operation in each thread. But there is a flexibility that you could operate on the same data or on different data. So that is not a problem with task parallelism. Okay, right. So with that, we will end our today's class with a few of the multi-threading models that are there, and proceed with the remaining part of the chapter in the next class. So the first multi-threading model that you can have is known as a many-to-one model, right? So in this many-to-one model, you will have only one kernel thread and multiple threads with this kernel thread. Now, can you tell me what could be a bottleneck for this particular model, many to one model? Any guess? No one? Let me help you with that. Say one of these threads, okay? It makes a blocking system call. So what happens when a
So
blocking
noise
system
আসতেছে
noise আসতেছে? এখন
আচ্ছা এখনো আসতেছে
হ্যালো,
জি স্যার
এখন ঠিক আছে?
জি স্যার এখন ঠিক আছে
আচ্ছা, okay, so যেটা বলছি, if you have this particular user thread marked in red, if it makes a blocking system call, what is a blocking system call? It basically says that whenever some process or thread is executing, no other particular thread will be able to execute on the kernel. Now, if this particular thread makes a blocking call, then it will be blocking the kernel from being used by other threads available in the system, which basically nullifies the benefits of having a multi-threaded architecture. Okay. Uh, to develop on this or to improve this scenario, what we do is we ensure we come to the one-to-one model where whenever you have a thread, you have a corresponding kernel thread. So it maps each user thread with a kernel thread, and it provides more currency compared to the concurrency compared to the many-to-one model. However, um, it creates overhead. What kind of overhead? The overhead of creating as many kernel threads to associate with the number of threads that you have. So it basically inhibits the performance of the particular um, system, right? So that is why we even though the one-to-one model exists in, let's say, a very um, bulk execution of any task, we try to avoid the one-to-one model. So to improve even upon this, that means to improve upon the many-to-one model and the one-to-one model, or if I rephrase my sentence, to overcome the limitations of the many-to-one and the one-to-one model, we come up with the many-to-many model. Okay, and this model, what it does is basically it has a pool of kernel threads which could be equal to or less than the number of user threads in your system, and each kernel thread can be servicing this particular thread. Now, there is one precaution, that is, um, in the one-to-one model, the precaution is for the one-to-one model. As a developer, you'll have to be careful that you do not create too many threads within an application. And in some cases, the system can put a maximum limit beyond which you cannot increase the number of threads in any multi-threaded system. Okay, but in case of the many-to-many model, the shortcomings are overcome. and the developers basically can create as many user threads as necessary, and the corresponding kernel threads can run in parallel on a multiprocessor. Okay, so now what if a particular thread, let's say this thread, creates a blocking system call with this particular kernel. It associates itself with this particular kernel thread. Now it should not inhibit, because you have other kernel threads at your disposal to service the remaining user threads in your system, right? So that is the benefit of the many-to-many model compared to the one-to-one or the many-to-one model. Now, this many-to-many model has a variation which is known as the two-level model. It basically says that we will implement the many-to-many model, along with we will also allow, let's say, having a particular thread associated with a particular kernel thread. Okay, now can you tell me when this particular type of scenario could be beneficial? Let's say you have a very high priority process that cannot basically wait for other processes to execute, finish execution. Again, you don't want to interrupt the already executing processes. Okay, in that case, what you could do is assign a separate kernel thread for that high priority process, so that you can seamlessly, or you can parallelly execute the previous threads or the processes, as well as the currently invoked high priority process. Okay, so these basically are the four thread models that you can implement in any multi-threaded architecture, each having their benefits and corresponding drawbacks. Any questions? No questions? Okay, so for today's class, since I have taken your attendance on, uh, through physical pen and paper, for today's class, as I can see in this meeting, there are 81 people. However, I have logged in from two different accounts, so there are in total 79 students. So I'll request the seers of both sections to um, submit the signed attendance sheet on Monday in respective classes for today's class. Okay, is it clear to you? I'll not take the attendance
Yes, sir.
in online, but you will provide me a physical copy of your attendance signed, and I will make sure that you don't provide proxy for anyone, because I have taken count of how many people are here in this particular meeting. All right. So if you have no questions, I'd like to conclude today's class. Okay. So thank you, everyone.
Thank you, sir.
Okay.